Hey everyone, this is Mr. Sal. This is a lesson on more representations of a linear context. Alright, you guys, let's just talk about some of this terminology, and I guess we can start with the rate of change. And we'll be exploring rate of change in a little bit more depth in a different lesson. But the rate of change, if we were to look at a graph, like this one, if we have some kind of line, say like this, all we need is 2 points on that line in order to find the rate of change. We just figure out how far up or down it goes, and then how far to the right, and then we divide those values. So we're looking at the change in y divided by the change in x for the rate of change. Y is over x's. In a context, it usually tells us something like $2 per hour, $5 per ride, 2 gallons per minute, something like that, okay? In tables, we find the rate of change between 2 points. So when it gives us values, then we say, well, what's the change in the y value? And then what's the change in the x value? And we divide those two values together to find the rate of change. And the reason why that's important is because when we write equations, they're generally in this form. Y equals the rate of change multiplied by the x, and then from there we would add the starting value. Now the starting value on a graph would be where the line crosses the y-axis, and the y-axis is this up and down one. On a table, it's where the x value is 0. Whatever that y value is going to be the starting value. And we've seen this before, all right? Now this is also called a y-intercept. And the y-intercept is always written as an ordered pair. And as we see in the table, it's always got an x value that's 0, and then whatever the y value is from this point on the graph. Now this is written as an ordered pair because it is an ordered pair on the graph. So today when it starts asking for the y-intercept, we're going to be writing them as ordered pairs and also in context. Okay? But the ordered pair should help us to figure out what it is in the context as well. That's just rate of change, and I guess we've kind of looked at the y-intercept as well. The y-intercept also is considered the starting value. So in past lessons, it's something like how much it costs to get into, I don't know, an arcade or something like that, or some kind of starting fee or starting value, okay? Like, for example, starting 43 meters away from a finish line. I think it was 42. For the problems that we'll be doing today, in each of the following problems, you are given one of the representations of linear relationships. So it's either context or a story, the table, a graph, or an equation. Complete the remaining 3 representations. Be sure to label the columns in your table and the axes on your graph. Let's talk about that as well, because they're not going to tell us, for example, in a table or in a graph sometimes, what the values are. Now we know in a table it's always the x values, and then on the left side of a table, and the y values on the right side of the table. In the past, you guys should have heard of this, whether it was in science or math. But your x values, these are called independent variables. Someone said they heard that in English too, or something like that. And the y values are, or the y's, are the dependent variables. Alright, so when we're looking at two quantities, we have to ask ourselves, does this value depend on the other one? Or is it the other one depends on the other one? Whenever we figure out which one is dependent, we know those are our y values. And whenever we figure out which one's independent, we know those are the x values. Generally, the x values are shown in some form of time. This isn't always the case, but when you see time is just going to, I guess, continue no matter what the other variable is. So, dollars per hour, right? If you get paid dollars per hour, the time isn't really depending on how much you get paid. You get paid depending on how much time has passed. So this will take some thought on our part so that we can figure out which is which. Otherwise, we're going to get them switched up, which is going to cause us to lose credit on those. So here's our first context. This is our first story. You and your friends go to the state fair. It costs $6 to get into the fair and $2 each time you go on a ride. Consider the relationship between number of rides and total cost. Take 1 minute to create the table, the equation, and the graph with your neighbor based on this story. All right. So on this one, I would make the table first on this. And just based on the stuff we just talked about with the independent and dependent variables, I can see that the amount of money, or the total cost, is going to depend on the number of rides that I go on. Okay. The reason why we need to know that is because I need to know which side the cost is going to go on in the table, and that's depending on the number of rides. So that's going to go on the right side of the table. Which means also that the number of rides would be our x values, which means it's independent, and would be on the left side of the table. Now here's the thing is, we know if you go on 0 rides, that's just entry into the fair. It said that it costs $6 to get into the fair, right there. So if I go on 0 rides and I just go into the fair, it's still going to cost me $6. But then it says it's $2 every time you go on a ride. So if I go on 1 ride, it's an additional $2 to the $6. So 6 plus 2 would be 8 if I go on 1 ride. And if we continue this pattern, $2 for every 1 ride, then if I go on the next ride, it would be another $2. The next ride, another $2. The next ride, another $2. And the next ride, another $2. All right, I'm going to do the graph next because we have the ordered pairs from the table. And we can label this because we know that the x is the rides and the y is the cost, so we'll label the x's right now. And then we'll scale this. So number of rides, that just goes up by 1 each time, so I'm going to start at 0, and we'll say it goes up by 1 for each line. So there's 5, 10, and 15. The cost, however, this one goes up by 2 each time, so I'm just going to say that each line represents 2. So there'd be 2, 4, there's 6, 8, maybe 2, 4, 6, 8, 10, 12, we'll put 10 on there. 12, 14, 16, 18, 20, 2, 4, 6, 8, and 30. All right, so from the table, we have the ordered pairs. 0 rides will cost $6, and also 1 ride will cost $8. 2 rides, $10. 3 rides, $12. 4 for $14, and 5 for $16. Next question is, what do we connect these points? No, because you cannot go on half a ride. Even though you could have, I suppose, half a dollar perhaps. By the way, this pattern also would continue because it is showing a straight line. So we could look at these other points if we need to. So to find the equation, we're going to write it from this form that we've been looking at. This y equals the rate of change times x plus the starting value. All right, so our equation is going to look pretty much the same. Y equals the rate of change multiplied by x. We just need the rate of change on this one. Let's see if we can figure that out. The rate of change is shown in the table between the values, which we've already looked at, right? For example, between 8 and 10, it went up by $2 for every 1 ride. It's shown in the graph between 2 points. It's going to go up $2 for this 1 ride. And in the context, they said it was $2 every time you go on a ride. So our rate of change is $2 for 1 ride. Now, we don't need to use the labels in the equation. We just know it's y equals 2x to start with. But then we need the starting value, which is just how much it costs to get into the fair, and that was $6. To be a little bit more specific, we're going to say $6 for 0 rides. So in my equation, I've got y equals 2x, and then plus my starting value, which is $6. And this right here would be the final equation for this one. All right, from this then, part A, what is the rate of change in this problem, and what does the rate of change represent in the context? We've already answered that. It's $2 for every ride. So just as an overall rate of change, that was 2 that we saw in the equation. 1b, what is the y-intercept for your graph? So this is the point where it crosses the y-axis, just like we talked about. And it's shown as an ordered pair where x is 0, which is in the table already. So the y-intercept would be 0, 6. And what does it represent? Again, we've already shown that. It's $6 for 0 rides, which again is shown in the ordered pair as well. $6, 0 rides. 1c, how would you change the context so that the relationship between the total cost and number of rides can be modeled by the equation y equals 2x? Well, yeah, I guess we see that right there. What that's showing is that the starting value is plus 0, which means that it would cost $0 to get in, and then you're just paying $2 for every ride. So it's free to get into the park. You only have to pay $2 for each ride you take. 1d, how would you change the context so that the relationship between total cost and number of rides can be modeled by this equation, y equals 6? Take 1 minute and talk about that with your neighbor. Yep, you have to pay $6 to get into the park, and then the rides are free. Again, they've taken away the unit rate, which was $2 per ride. So we're not even multiplying it by x, it's just y equals 6. Y is the cost, by the way. So it should help us understand the cost is $6, and then we're seeing there's no way to change that value. So on this one, it's just $6 to get in the park, and then rides are free. Number 2, here's the story. You are taking a road trip. You start the day with a full tank of gas. Your tank holds 16 gallons of gas. On your trip, you use 2 gallons per hour. Consider the relationship between time and hours and the amount of gas. Again, it's given us the 2 quantities. We've got to determine which is dependent and which is independent for the x and y's. But take a few minutes with your neighbor and see if you can complete the table, graph, and equation on this one. The 2 things that we're comparing on this are, it just says at the bottom, consider the relationship between time and hours and amount of gas remaining in the tank. This one gave us a time on this, so we should know right away that time is always going to be our x value. So I got time in hours, we'll put hours, for our x's, and the y values going to be amount of gas in the tank, which is in gallons. So yeah, I'm starting with the table first. Not that you would necessarily have to. But the number of hours, let's say we're at 0 hours. At 0 hours, it said that it's starting with a full tank of 16 gallons. So that would be 16 right there. Then, as the time goes on, it's 2 gallons per hour. So after 1 hour, it should burn off 2 gallons, and you'd be left with 14 on that. Then after another hour, you'd burn off another 2 gallons and be left with 12. 3 hours then would be 10, 4 and 8, and then after 5 hours you burn, or you have left in the tank, 6 gallons. Now once again from the table we should be able to do the graph. And again we see that the x value will be hours because it's the left column. And gallons will be the y-axis. Next up, we'll scale the axes. So number of hours, we'll just let this go by 1 each. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and up to 15. And then the gallons will start at 0. On this one, just to make it fit, I'm going to make each line worth 2. So there will be 2, 4, 6, 8, 10, 12, 14, 16. That's as high as we need to go for the gallons because we know that it's going to start at 16 gallons. So on this one, let's go on and graph the points. Starting with at 0 hours, it's 16 gallons. Then at 1 hour, 14 gallons. 2 hours, 12 gallons. 3 hours, 10 gallons. 4 hours, 8 gallons. 5 hours, 6 gallons. Now I'm going to continue this because it's on a linear pattern. So at 6 hours, it should be 4 gallons. 7 hours, 2 gallons. And then 8 hours, 0 gallons. Which means if we were going to run the tank dry, just based off of the full tank and burning 2 gallons per hour, it would take 8 hours to use the whole tank on that. Next question, some of you guys answered this. Would we connect the points? We would on this one, yeah. Because you can have half an hour, and you can have half a gallon as well. So the rate of change on this one, so that we can write the equation, we see that it's 2 gallons for every 1 hour, but it's 2 gallons used, so we have to show that it's negative because it's 2 gallons that are going away on this. So the rate of change on this one will be -2. And the starting value, it's starting with a full tank right here at 16 gallons at 0 hours driven. So the starting value would be a positive 16. So just to finish the equation, we got y equals -2 times x plus 16. There's our equation. So we've taken care of the other 3 representations, table, graph, and equation for this particular problem, but there's other problems with this. 2a, what is the rate of change in this problem? What does the rate of change represent in the context? Yeah, we already saw the rate of change is -2 gallons per hour. So the rate of change would be -2. And yes, it's shown in the equation with that -2 right there. Part B, what is the y-intercept of your graph? We know what it is represented by. It's 0 hours for 16 gallons. So we just need to write that as an ordered pair. 0 hours, 16 gallons. Bam. That would be the y-intercept or the starting value. Part C, how would you use your equation? How would your equation change if your gas tank held 18 gallons of gas and used 2.5 gallons per hour of driving? What would these changes do to your graph? Take 1 minute and talk about these two with your neighbor and see if you can figure out what the equation would be. All right, here's the next problem, but this one does not give us a story. which means you're going to have to write one up. So they do give us a table though, which is a good start. So using the table, make the equation and the graph, and also write a story about it, okay? Take a few minutes to do that with your neighbor. So first off here, with the table, and we can write the context after we get the equation and the graph on this, by the way, which would be fine. So from the graph then, I know that the x-axis will be labeled as time, because it's the left side of the table there. And the right side is cost, so that's going to be our y-axis. So time, it goes up by 1 each, so I'm just going to say that each line is 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And the cost will start at 0. And it looks like I'll go by, actually I'm going to go by 2 each for this one. So it'd be 2, 4, 6, 8, 10, 12. All right. From this, we have the ordered pairs from the table. At 0 hours, the cost was $7. Now this is $2 for every line, so I've got to go right between the 6 and the 8 right there. Well, tried. The next one would be 1 and 9, which would be between 8 and 10. The next would be 2 and 11, which is between 10 and 12, right there. And so forth. So 3 and 13, 4 and 50, and 5 and 17, right there. Now, of course, just looking at this one, it's a linear pattern, so we would expect this pattern to continue like this. And what do we connect these points? Well, cost is in dollars and time is in hours. So yeah, it looks like we would connect these points with a straight line-ish. All right, for the equation, let's figure out what the rate of change is. I guess for that, actually, we may need to figure out the context for this one. And there's several different ways to do this one. Yeah, that's a good one. So if we use this context, which will change how we have to write the rate of change for this one. Then the rate of change for this one, it already said that it was $2 every 1 hour. So in the equation, I will take the rate of change as 2 for $2 per hour. The starting value is that they're going to charge you $7 for 0 hours. So the starting value, or the starting cost, is 7, and we can fill in the rest of the equation. Y equals the rate of change 2 times x plus the starting value, which is 7. So this would be the equation for it, and we have the context already. Last thing we'll want to cover on this one before we look at the other parts is the y-intercept, which is the starting value. That's 0 hours, will cost $7. And that would be the y-intercept. We can see the y-intercept on the graph where the line crosses the y-axis. At that point, again, is at 0, 7. So we did part A and B by answering the rate of change in the y-intercept and starting values. Part C, how would your context change if the rate of change was 3? So in the context that we had, So the context that we had a rate of change at $2 per hour. This one's saying the rate of change now is 3. So instead of it being $2 per hour, this would change into a $3 per hour. For this one, they only give us the graph, so we got to figure out the rest of this from that. And we can figure out just from the graph. Let's take a closer look here. On the graph, we can see that the starting value, or the y-intercept, is right here, where the line crosses the y-axis, and that is at 0, 100. Now that's going to help us with the equation as our starting value right there. And also, the rate of change, I can see this, I've got this point right here. It's going to go down 10, and then to the right 2, whatever these are, because we haven't labeled them yet. So the rate of change for this one was down 10, and then to the right 2, which simplifies to -5. The starting value for this one is 100. So this allows me to make the equation y equals the rate of change, which is -5, multiplied by x, and then plus the starting value, which is positive 100. From here we can do the table, and I know x is going the left and y is on the right. And if I start with 0, 100, which is the starting value, then the next one was at, when the x is 2, then the y is 90, so 4, y is 80, x is 6, y is 70, x is 8, y is 60, and finally x is 10, y is 50. And I'm just identifying the ordered pairs of these points. Next up we need some kind of context on this one. This is the context I came up with. And this would be good enough. I start with 100 sandwiches and eat 5 sandwiches a day, which is that -5 stuff. And I'm going to do this. It looks like from the graph I would end up with 0 sandwiches on day 20. So it would take me 20 days to eat all 100 sandwiches. How would your context and equation change if the y-intercept of the graph was changed to 75? For me, it would just be that I would start with 75 sandwiches instead of 100 sandwiches. That's it. How would your context and equation change if the rate of change in this problem was changed to -2? The context would be that instead of eating 5 sandwiches per day, I would be eating 2 sandwiches. So the equation on this one is just changed. We're still going to start with 100 sandwiches. But now the rate of change is 2 sandwiches per day. So multiply that by x, the number of days. For this one, it gives us the equation. From the equation, we need to fill in the table, the graph, and then also write a context for this one. We'll give you guys a few minutes for this. So all we're given is the equation to start out with. What we do see on this is the rate of change is 4, and the starting value, whatever the context will be, is 10. Which means as a y-intercept, it would be 0, 10. Which also allows us to get started on the table, which will have x values on the left, y values on the right. I'm going to skip that first row so that we can put a label in there once we figure out what the context is. But I know when x is 0, y is 10, because that's our starting value, just based on the equation, because we got plus 10 right there. Now with the rate of change, as we've seen before, this one is 4. We could kind of show it as 4 over 1, which means for every 1x, you're going to get 4 y's. So if I increase x by 1, I've got to increase y by 4. And this pattern will continue. As I take another x, I need 4 more y's. Another x would mean 4 more y's. Another x and another 4 y's. And the last x with 4 more y's. Now, again, we don't have context for this. We don't have labels yet, but we will. So I'm going to go to the graph now. And I know it's x and y. We'll label those later. For the x's, I'm going to start at 0. And again, these will each represent 1. So there's 5, 10, and 15. And the y values, this one goes up to 30. So I would say that each of these represents 2. So 2, 4, 6, 8 is 10. 12, 14, 16, 18, 20. And it goes all the way up to 30, which is as far as we need it to go. From the table, I'll put these points on there. When x is 0, y is 10. There's a different color for that. When x is 1, y is 14. When x is 2, y is 18. When x is 3, y is 22. When x is 4, y is 26. And when x is 5, y is 30. Now, whether we need to connect these points or not, we don't know yet because we don't have a context for it. So I will make one up, whether you guys like it or not, sorry. Okay. So on this one, I'll start with whatever I started with. So I'll say I started with 10 sandwiches. And then made 4 sandwiches. Yeah, we'll say sure, we can say every hour. And actually, that's probably as far as we need to go on that. Because we continue and it doesn't really say when it stops on this. Now, based on this scenario, if we looked at sandwiches in hours, the number of sandwiches would depend on the hours, which means the hours would be the label for the x-axis. And the y-axis would represent sandwiches. And also, we would not connect these points because you can't have half a sandwich on that, okay? Now, you could say you have half an hour, but if we're going to say we'll just go with full sandwiches. Now, if you wanted to, you could put points in between these, like right here and there and there, because at those half-hour increments, you would have an extra sandwich, or 2 sandwiches, rather. Also, we'll need to change the rest of the stuff, so I need to put the labels in the table. And then the starting value, we already put the y-intercept on there. That would be 10 sandwiches just to start with. So 5a, how would your context change if the equation above was changed to y equals 2x plus 10? How would this change affect the graph? On this one, since we were making 4 sandwiches every hour, this one would only be 2 sandwiches per hour. But it still shows that we would start at 10, so it would be, it wouldn't be as steep. So let's show that on the graph, right? We would have this point at 10 sandwiches, but then it's 2 sandwiches every hour. Again, this line is just not as steep on the graph. On this one, how would your context change if the equation above was changed to 4x, y equals 4x plus 8? On this one, you're just starting with less sandwiches, but you're still making them at the same rate. So the line would have the same steepness on the graph, but you're just starting with fewer sandwiches. All right, number 6, describe in your own words what a linear relationship is composed of. Think about all the equations that you have written to represent a linear relationship. What do they have in common? What do the different parts of the equations represent? So it's a linear relationship is described by taking an initial value or starting point, y-intercept, and adding the rate of change times x. So take a minute and write that down.